Welcome, colleagues. Welcome to the SAMPI Space Applications Technical Committee webinar series. My name is Raj Manchanda, and I'm the Chief Technology Officer of SAMPI North America. SAMPI is the Society for the Advancement of Material and Process Engineering. Please, if you can, please enter in your name, your company name, your geographic location in the chat so we can all introduce each other. Thank you. Again, welcome to the SAMPI Space Applications Technical Committee webinar series. My name is Raj Manchanda, and I'm the Chief Technology Officer. I'm accompanied by Ms. Rocio Figueroa as Program Manager. Welcome to the webinar. Thank you so much for joining. Please, as I mentioned in the chat, enter in your name, your company name, and your geographic location. Thank you, folks, for joining. Please, again, thank you for joining this webinar, and we are going to start shortly, but for now, let me just go ahead and keep sharing our slides, introductory slides. SAMPI also has these technical committees that we've launched, and you will hear a little more about them today, but for now, we have 7 technical committees. You can join anyone, whether you're a member or a non-member, on SAMPI's 365 platform. SAMPI's 365 platform is an easy way to communicate. As you see here, we have 7 technical committees. One of the upcoming projects of the technical committees is this emerging trends panel coming up at CAMEX Atlanta. We hope you will join us. That's Wednesday, November 1st. All the technical committees will present their emerging trends within each technical focus area. The State of the Technology Industry Report is another product of the technical committees. As folks who are on this call, we hope that you will join one of the technical committees, especially TC7 Space Applications, and contribute to the next one. You can download your copy from the SAMPI online store. It's nasampi.org. Thank you, folks, for continuing to introduce yourselves in the chat. Please continue to do so. We're really grateful for you joining this webinar. There are sponsorship opportunities available, so as you go back to your management, please go ahead and consider sponsoring a future webinar. My colleague Jordan at sampi.org, please contact Jordy at jordan@sampi.org. That's JOURDAN at sampi.org for further information on sponsorship opportunities. This is a lineup of the upcoming webinars that we have. Just so you see that, this is Space Applications webinars. Bear with me. I want to introduce our speaker today. Today's presentation is on materials engineering enabling space exploration in the most extreme environments, which is featured Dr. Dan Polis, Vice President of Engineering at Sierra Space and Vice Chair of the Space Applications Technical Committee. Other leaders of the Space Applications Technical Committee include Dr. Chris Fleming of Northrop Grumman, who is chair of TC7, that's the Space Applications Technical Committee, and Mr. Jaden Palick, PhD student at the University of Nebraska at Lincoln, who is secretary of TC7. As mentioned previously, SAMPI currently offers 7 technical committees, and we invite you to join a technical committee that matches your interest on SAMPI's 365 community platform. The TCs provide year-long education and networking opportunities for experts, newcomers, early career professionals, and graduate students. In addition to SAMPI's chapters, The technical committees offer a convenient way to get more involved with SAMPI. The technical committees typically meet virtually for 1 hour each month and twice a year at person at the SAMPI Spring Conference upcoming from May 20th to 23rd in 2024 in Long Beach, and CAMEX, which is days away, and that will be held October 30th to November 2nd in Atlanta. The CAMEX team is pleased to report that 500 plus exhibitors will be showcasing their M&P equipment and industry solutions in Atlanta. We hope to see you in Atlanta with several thousand M&P professionals and students from around the world. SAMPI members and non-members can join a technical committee of their choice on SAMPI's 365 community platform. One output of the technical committees, as mentioned previously, is the State of the Technology Industry Report. It's available for download at no charge on the SAMPI online store on nasampi.org. Please visit, and we invite you to contribute to a future SOTAR if you join one of the technical committees. Technical committees consist of global participants from industry, academia, government, and offer a convenient platform for all to learn, network, discuss trends, and collaborate on industry solutions. Now let's welcome Dr. Dan Polis from Sierra Space. I'm going to give a brief introduction. Dan has been with Sierra Space, previously part of Sierra Nevada Corporation in Louisville, Colorado, since 2012. He currently serves as the Vice President of Engineering, where he leads an advanced manufacturing materials and process group. The group is responsible for materials assurance across all business sectors, materials development, and advanced manufacturing, with a focus on integrated composite structures, reusable thermal protection systems, and additive manufacturing. Prior to this role, Dan served as the director of Dream Chaser cargo system spacecraft, where he managed a team of engineers responsible for the design of a spacecraft planned for orbital flight, International Space Station Services, re-entry, and reuse. Dr. Polis also spent many years as spacecraft design manager and structure subsystem lead for the Dream Chaser program. Before coming to Colorado, Dr. Polis worked 10 years at NASA's Goddard Space Flight Center in Greenbelt, Maryland. At NASA, he played an integral role in the development of several one-of-a-kind composite structures, including the NESC's Composite Crew Module, the cryogenic composite metering structure on the James Webb Telescope, and the super lightweight interchangeable carrier, which carried the Hubble Space Telescope's new instruments to low Earth orbit on STS-125. Prior to NASA, Dr. Polis worked for General Electric, where he was program leader for the Ceramic Technology Group in the Lightning Division in Cleveland, Ohio. Dr. Polis has a MS and a PhD in materials science and engineering from the University of Pennsylvania and a BS degree in chemistry from the College of William and Mary. Dan, welcome. Thank you so much.
Thanks, Raj. I appreciate it. I appreciate that intro, and I'm glad to be here. I see a lot of former colleagues. I see some folks I worked with on James Webb on the list, which is fun, and some current colleagues, some former interns. So thanks everybody for joining. Raj kind of gave my background. I kind of inserted this one line on when I was introduced to SAMPI. So, after coming out with a PhD in material science, kind of fundamental polymer science, I didn't know anything about composites or aerospace. I worked at GE Lighting for a few years, and then when I joined NASA, SAMPI was a great introduction to kind of know, what materials were used in space. That's where I learned, composites, and started to present the work at Goddard. I'll highlight some of that. I encourage a lot of folks, if you're not already a part of SAMPI, it's a great way to get introduced to aerospace and aerospace materials. So for those who haven't heard about Sierra, I'm gonna, a lot of the discussion today will be what we're doing to commercialize space. So our mission is pretty bold. We're building a platform in space to improve life on Earth. And here you can see a depiction of a future commercial space station. And you can see berthed and docked various Dream Chaser vehicles, which I'll talk about. So a pretty big endeavor. We're pretty far along on our Dream Chaser transport vehicle that will be used to go to the International Space Station, but I'll talk about some of the next steps that we have planned. So first, Sierra Space is really set up in three primary sectors. Space transportation. So our goal is to simplify transportation to and from space, and really targeting the lowest cost cargo and crew in the market segment. So of course, our claim to fame is we can land on any runway really in the world, short runway landing, a low G landing to bring science experiments back, and the astronauts that we have working here think that's really, the way to do space travel. Our space destination. So while our space transportation business is targeted at serving a NASA customer today, we want to really emerge as the largest real estate developer in space. So building a commercial space station where folks can develop new materials, they can look at how drugs or how health helps heart disease, for instance, where microgravity could be an advantage. So we want to provide that infrastructure so people can bring up experiments, do whether that's pharmaceuticals or new material development. And of course, we need transportation to get there. And then finally, our space applications business. We've really built over 25 years of space applications business, whether it's high precision mechanisms, power systems, and now we're building really the next generation of differentiated technology. Shown here is our cargo module, which is ready to go to NASA's Armstrong test facility here this month. And really high value Earth observation and on orbit servicing constellations as well. So for those of you who don't know about our history, I thought I'd start a little bit with the origin of our transportation sector. I think it's pretty interesting. Really dates back to the early 1980s when when Russia flew the Bohr 4, pictured here, actually reconnaissance images from the Australian Air Force. NASA took those images and started to develop an HL-20 lifting body aircraft. And then in the early 2000s, a company called Space Dev started to take that HL-20 concept and put it into how do we use this concept to provide access to low Earth orbit. That company, Space Dev, was acquired by Sierra Nevada Corporation, which Sierra Space spun out of. And we modified that HL-20 design into the Dream Chaser spacecraft. When I joined in 2011, we had already been awarded several development contracts. And at that time, it was to provide human-rated access to the International Space Station. Ultimately, we did not win that contract, but we did perform some significant flight tests. So here in 2013, you can see a drop test article, our engineering test article, which was dropped from 10,000 feet. Then we pivoted when we didn't win that human-rated contract to a cargo vehicle. And we modified the vehicle to have folding wings. We removed the windows, we got rid of the abort system, added a cargo module, and put it on top of a rocket under a fairing. We ultimately won the CRS-2 contract, which is to provide cargo services to the International Space Station. And we've been developing that product ever since. In 2018, we had several critical design reviews, and a major hardware milestone in 2019 was the primary structure arrived here in Louisville, Colorado. I'll show some pictures of what it looked like back in 2019. We then kind of in the interim spun off Sierra Space from Sierra Nevada Corp to be an independent commercial space company. And now we're slated to fly in 2024 to the International Space Station. So earlier this year on the cover of Aviation Week, you can see the orbital flight vehicle. This is undergoing static tests, so wing bending occurring here, also kind of overall body bending tests and pressure. So what I want to really highlight is, over the last decade, the chemistry and physics, of course, hasn't changed to go to space. But really what I've seen coming from NASA to commercial space is we're really trying to make it more accessible, which adds a new constraint, to do it affordably, to do it quickly. Some of the tools that M&P engineers use, things like digital image correlation or manufacturing methods like additive manufacturing, are really enabling us to speed up and optimize systems. And that's really what I'll highlight in the talk today. But before I do that, for those of you that may be new to, why is space hard, at least from an M&P perspective, really go to, so this is a picture, right, of low Earth orbit. Here's L2 where James Webb sits. There's many challenges, but I think a lot of them come down to the mass challenge. We have to decrease mass to be able to launch it off from Earth's gravity. So every problem that we try to solve, we have to optimize. You think about building a bridge, you can throw as much steel at it as you want, but we're not able to do that. And so when you want a really stiff metering structure, you have to do that with lightweight materials. Vacuum stability, of course, adds extreme challenges to polymeric materials. And I would say what I see as the largest driver, and certainly in the two applications I'm going to talk about today, are the temperature extremes. So James Webb, for those that follow it, is at minus 251 Celsius, or at least its survival temperature. And a lot of the testing we had to do, to show that things could survive. And then Dream Chaser's at the other end of that extreme, re-entering at nearly 3000 F or 1650 C. Certainly combined with that, there's other challenges. The thermal cycling aspect in low Earth orbit makes it extremely challenging. Micrometeorite debris impacting, and concerns with impacting pressure vessels, atomic oxygen and radiation, either protection or shielding. So all these, couple into how do you solve this problem for low mass, do it affordably, and do it in a reasonable amount of time. So I wanted to start out, actually, I pulled from a paper that we published at SAMPI in 2006, but I thought it was relevant. And I have a few lessons learned. People don't think of James Webb as, oh, there's lessons learned for commercial space, but I think there are some. And so I wanted to start with some very high level examples. So despite, the James Webb considerable budget and schedule, the team didn't have sufficient time to develop a new composite prepreg system. Those systems take a very long time. And so even, that would have had to start 10 years before the James Webb system. We had to pick up an existing system, but we optimized performance of a cyanate ester material system for cryogenic performance. And so here is a plot. On the left is mean flatwise tension strength of a laminate. On the right is what we term cryogenic durability, so the inverse of the microcrack density. And what we showed is that by varying the degree of cure, same material system, but by not curing it all the way, essentially, we could get peak performance for these cryogenic temperatures. And, that's published in the SAMPI paper, but, the whole, I wouldn't say the whole, 90% of the composite portion of the observatory was undercured intentionally. And so the real takeaway there, that I tell folks on my team here is you can't engineer by specifications, because specifications are created for standard applications. And certainly James Webb and Dream Chaser are not standard applications. So, this is a picture of kind of microcrack density. If you really look at the time that those occur, they occur during, each cycle, and you want them to be stable during, so where the structure is. And so the takeaway here is, understand the performance you need, and then you as the materials and process engineer, define what's acceptable. Two more James Webb examples really briefly. So first, this is an example of really thinking out of the box to come up with a faster, more accurate technical approach. So on James Webb, we were faced with, all materials needed to be characterized from room temperature down to near absolute zero. And things like strain gauges just weren't a viable approach. They weren't very accurate and they were costly. And we wanted really continuous characterization. So one of my colleagues at the time found this mathematical formulation from the 1930s that basically said if you vibrate a plate, the first two modes, this X and O mode, will give you uniquely Poisson ratio by taking the ratio of those two modes. So we created what I call an elastic property cryogenic analyzer, basically a non-contact electromagnetic vibration system that we could scan, cool the sample down and scan elastic properties the entire way. And we showed that this was very accurate and actually showed some errors in NIST papers where Poisson ratio was assumed to be something and it was incorrect. So, really thinking out of the box for an inexpensive method. And so I encourage people to use other sources outside the traditional aerospace field. So again, if you're new to aerospace, you may be bringing things like from the automotive industry that haven't been done before in aerospace, and that's what we need. Next, probably preaching to the choir when I talk to engineers, but understanding the physics of the problem is important. A good experiment requires theory to support the results. I think the complexity with that statement is you should develop a model to predict your experiments, but what level of complexity is a lot of times where there's a lot of cost. We may spend 2 years to create a model only to show it doesn't agree to experiment. And so really, I think iterating, starting very simply and using experiments to compare. So on the right here are our thermal expansion measurements that we did for James Webb. We started at the coupon level, and what we found when we went to the box beam level, which is what the ISOM structure on James Webb was made from, our results didn't agree to what we expected, but the finite element models predicted some very subtle effects that were not necessarily intuitive. So first, that the tubes, because of the closed form nature of them and the difference in CTE of through thickness versus circumferentially, got this butterflying effect. As well as the edges curled in, which you didn't see on flat coupons, to relieve that thermal residual stress. And that gave us artifacts in our measurement. So again, if you looked at a 6-foot tube, you wouldn't see that, but we couldn't really understand why we're seeing that in short coupons. And so we were able to reconcile very accurately the thermal distortion once we ended up building that model. So now moving into commercial, again, the ideas that I was presenting from James Webb is how do you do it quickly? How do you move more rapidly than the traditional, I'll say the traditional NASA model, even though I just presented NASA examples, but that's what we're always looking for in commercial space. In my group, these are 4 areas of where materials plays a key role. So first, for composite assemblies, in trying to enable the affordable development of complex outer mold lines. So again, a re-entry vehicle has a very unique shape. Composites allow you to do that relatively quickly with a small number of tools. We also try to reduce part count, and there's several reasons for that. We use 3D woven joints to eliminate fastener penetrations, both through the pressure vessel and lower air shell. And then composites can enable higher temperature outer mold line or bond line temperatures to reduce the thermal protection mass. So thermal protection systems, right? We have to insulate the structure and everything inside it. So for a reentry vehicle, we need a stable outer mold line. So we at Sierra Space don't use ablatives like you may see on capsules. And then other areas, hot structure is another avenue where we can provide weight savings and increase durability by removing traditional insulative tile and going to hot structure. Additively manufactured parts out of metallics is a big thrust of ours to reduce lead time and cost for many aerospace alloys. In some cases, and I'll present one, additive manufacturing can lead to improved properties over wrought products. And then some other modern tools like additive couples well with topology optimization or build to scan, right? Where you're going to want to get the as-built, scan it, and then print it. That rapid turnaround is advantageous with additive. And then for design, as I'll talk about for some propulsion areas, additive can enable things that aren't possible with traditional manufacturing, like embedded channels. Then the last area I won't talk about today, but I thought was worth highlighting, soft good development is a key area for us in our commercial space station, specifically our large integrated flexible environment or LIFE platform. And key drivers here, as I already talked about, permeability, radiation shielding, creep, MMOD protection are all key design parameters. So from a composite assembly perspective, at the core of the Dream Chaser body assembly is basically a bonded integration of nearly 150 parts using 1/4 mile of advanced 3D woven preforms. So, there's several aspects to this. There's the manufacturing part of this to produce it. There's the non-destructive evaluation to show that what you produced is consistent with your coupons. And then the certification efforts that go along with that, how to show that you have sufficient life, how to show you have sufficient strength. So a lot of design challenges, but why do we do it? Decreased mass, elimination of tooling required to create some integral return flanges. So again, this upper lattice is bonded to a bulkhead. We removed tooling by not having a bolted joint there that we had to create tooling to make that return flange. We were able to decrease penetrations through the pressure vessel and decrease penetrations through our lower air shell. Kind of a highlight of performance. So this table shows this woven architecture in a T-joint, and we compare it to equivalent weight sections. So a traditional metallic skin, metallic web, or a composite skin metallic web. And we made these kind of all equivalently weight size. So again, if mass is the object, how do they all perform? So first, from a part count perspective, as folks may know, procuring fasteners and collars add up in terms of management, grip length, things like that. So we're able to eliminate part count. Manufacturing process, while fastening has been around for a long time, there's lots of processes to do that for highly critical bolted joints or riveted joints. Versus a one-step co-bond. Again, there's a lot of process control required to get here. And if we look at the normalized ultimate capability, we see that the woven preforms are 2.4 times stronger than the equivalent weight metallic. And from a fatigue perspective, even better. Again, for this reusable vehicle, that was key for us. And that we basically go to run out at 37% ultimate versus 59,000 cycles or 200,000 cycles for these other joint options. Moving into thermal protection systems, here you can see some of the vehicle progressed later than that aviation week cover with tile both on the pressure vessel as well on the aeroshels. So we have over 2,000 insulating tiles which protect Dream Chaser during re-entry. Other components that are key are strain isolation pads between tile and structure to decouple overall vehicle deformation. We have micrometeorite debris enhancement fabric. So to protect the pressure vessel and critical hardware, we enhance these tiles for MMOD protection. We have aramid felt for our lower temperature applications where tiles not required. And then compliant thermal barriers at key interfaces like our deployable wing interface. So from a TPS development perspective, we've really invested significantly, and kind of the strategy is start with vertical integration. So Sierra Space is vertically integrating fabrication of our insulative tile, which really started with NASA, and NASA's still producing tile for commercial partners. And so we have a pilot plant here in Colorado and full-scale production ramping up in Florida. Similar to the vibrating plate on James Webb, some innovative test facilities that we've built is we've used our rocket engine technology to make a rocket jet to mimic the space environment at a low cost. This enables us to screen TPS materials prior to going to costly government arc jet facilities, for instance. And we can continuously expose materials to hydrogen and oxygen stream at 3400 F for 8 minutes. And this is located at our Madison facility in Madison, Wisconsin. So we can't necessarily do everything alone, and we have some key partnerships with Department of Energy and NASA to improve our two-part insulative tile. That's our highest performing tile. You can see an example of our two-part tile here. And so the product evolution is vertically integrate, incrementally improve through materials engineering to produce our TPS 2.0, and then replace TPS eventually with hot structure in critical locations for vehicle performance and durability. So moving into the last area that I wanted to discuss was additive manufacturing. So Sierra designs, tests, and manufactures thrusters for a large range of space applications, including 26 thrusters for the Dream Chaser and cargo module. This is a higher performing engine here from a recent contract that we won. And really Additive's game changing here from really reducing technical complexity. So reducing complex machining, reducing complex welding, and the inspection associated with both of those. In some cases, additive manufacturing can increase performance over wrought products through controlled microstructure. I'll say that, this is maybe not the norm. We're typically looking at speed and cost more so than performance. But here's an example where we see by controlling grain structure, we can use laser powder bed fusion production of C103 for our RCS system and get unique microstructure when compared to C103 in the raw form. So these top are as printed, and after 2 hours at 2900 versus the raw products, similar heat treat. You can see grain growth significantly here. And then mechanical properties, both ultimate and yield strength increases. And then room temperature versus 1400 and 1800. So the real takeaways that I see moving into on the commercial side is that materials engineering is critical for space exploration, but now I would say it's probably equal parts help improving schedule, cost, and technical. So on the schedule side, I talked about reduced part count and fastener installation with 3D woven joints, or eliminating machining and welding through additive manufacturing. On the cost side, elimination of complex part tooling with 3D woven joints, or extending reusability through increased TPS thermal stability. And probably what most engineers focus on is performance. Certainly we get increased performance. I showed increasing, well, I actually didn't talk about increasing bond line, but we can increase structural bond line temperatures to reduce TPS mass through material selection. Or we can increase static strength from optimized additive grain structures. And I presented some other ones as well. So before I take questions, I did want to say, I got pulled into TC7 by a former colleague, Lenitra Tate, who I met at NASA. She recently asked me to join and help out space applications technical community. I've since met Chris Fleming from Northrop Grumman, someone who my circle and his circle had never overlapped, but it kind of highlights, even after you've been doing this for a long time, I think it's great to continue to network. Why? Well, when you build your network, it can really aid in finding solutions to the problems you have at work. So again, this has already led to several non-disclosure agreements and discussions on problems that we have here that I could use help, as well as it's good for recruiting or being recruited. So if you're kind of new to the aerospace industry and aerospace materials, it's a way to reach out and meet people. hopefully learn some state-of-the-art AMP technology, whether I talked about that today or certainly in our upcoming series where a lot of NASA experts will be here talking about their area of study. And then you have an opportunity to share your organization's work. That's good if you're a startup or you're just trying to get your name out. And then we're also producing a state of the technology industry report for TC7. And so the more people that we have participating in that, the better, to get a mixture of government, industry, and academics. Here are contact info for Chris, myself, and our secretary, Jaden. So feel free to contact any of us if you want to learn more about joining Space Applications TC. And with that, be happy to take any questions.
That's great. Thank you so much, Dr. Paulus. Dr. Fleming, Chris, are you available? Did you want to say any closing remark or anything? Chris is on travel, so we're not sure. Okay. All right. But again, thank you so much for that excellent presentation. We have a few questions in the chat, so I'll address those. This one's from Felix Chen. Felix is, by the way, our co-chair of our TC2, I believe, Bonding and Joining Technical Committee. So thank you so much, Felix. On understanding for cryogenic applications, how does that help? I'm thinking undercurring reduces brittleness and hence increases mechanical dissipation that diffuses stresses at the microcracks at cryogenic temperatures.
Yeah, I think two things. So one, by lowering the TG, you have less thermal residual stress during cure. So that's kind of one, reducing the internal stresses. And two, really increasing the toughness. So allowing for more polymeric migration allows dissipation and increased toughness.
Excellent. Thank you so much. We have another question from somebody in the audience. What types of materials are being investigated for use in hot structure?
I can't really talk about specifics. You could Google it and probably come up with some papers there, but that's I can't really get into any specifics. Sorry.
Okay, thank you, Dan. Here's a question from Bjorn Balian. Can you speak more on the 3D preformed joint and composite skins?
Yeah, so I can't get into our specific use, our specific architecture, or our specific materials. I will say that it's built off a lot of good work that's been done that is some of it public. Most of it is ITAR restricted. Depending on your ITAR, I guess. If you're a U.S. citizen, I could possibly share more, but I can't share it publicly.
Okay, thank you so much. Here's one from Travis Alley. When not fully curing your polymer to increase its cryogenic performance, how do you prevent the polymer from finishing its cure when exposed to elevated temperatures in the space environment?
Yeah, that's a good question. I mean, James Webb was pretty unique. And so, it's not really getting very hot on the cold side of the observatory. So it was still cured at much higher temperatures than it would ever see during its use case. So we really didn't expect or anticipate that any additional curing would occur. I mean, the kinetics are so slow. Theoretically, they're still progressing in cure, but really not over the lifetime of the observatory.
Thank you, Dan. Here's a question from our colleague in India, 10,000 miles away, Raja Shyam Radhakrishnan. Can you share your points on reusable rockets in terms of sustainability? And Dan, before you address that, I wanted to ask you, do you think this whole reusable rockets, as it's been introduced to the industry, has that been a turning point for all this interest in space applications on, possibly on the consumer side?
Well, I guess what I'll say is the reusable rockets, and so again for us, primarily we're not a launch vehicle provider, so we're buying a ride from one of the industry partners, whether that's ULA for our first ride or others out there. But reusable rockets are driving down the cost per launch for everybody. And so
Right.
that's a great advancement for everybody in the industry and to really commercialize low Earth orbit, because that is a big, if you look at the Pareto of your cost, that is one of the biggest ones. And so, every time we see a successful return of first stage, we're excited, even if it's our competitor, because that brings down launch costs for everybody.
Excellent. And Roger Shyam's point about the sustainability piece, I mean, that's even more important nowadays than anything. We all know about climate change, and sustainability is a big part of everyone's conversation.
Yeah, and huge material challenges there, every time on how does that drive life, what inspection points are needed. And so I think it's getting kind of aerospace materials people to think a lot more, borrow from the aircraft industry, to borrow from the automotive industry on, how do you certify life, what parts can be, have maintenance on them each flight versus which ones have to be designed for, maximum reliability.
Excellent. Thank you. Here's a question from Romain Martin. What is the share of thermoplastic composites versus thermoset in your projects? Do you see this ratio evolving in the coming years?
Well, this is a great topic that I think TC7, I'm hoping to learn more about, and through the other TCs, there's a thermoplastics TC as well. So there's a big push right now at NASA. This is a technology thrust to study thermoplastics. I see, two areas in aerospace. One is we need to start thinking in cycle times of minutes rather than days when we produce parts. So that's more of an automotive mentality. But if we want to drive costs down, going into an autoclave for 12 hours is not cost effective. So that's kind of terrestrial applications, and there's several products that we have that we'd like to move to those quick cycle times. But then that can if you think about a technology roadmap, ultimately we'd like to see in orbit manufacturing. So rather than have to make a solar array stiff enough so it can handle launch loads, if you could extrude, or if you extrude a solar array on orbit, it could be much lighter. And so that's kind of one of the next gen things. So both of those sides. I think I right now I can't break down the share of thermoplastics, but in my experience, it's very low compared to thermosets. And really, I think this is an emerging area.
Excellent. Dan, you had mentioned something about the other technical committees. For those of you on our webinar today, you may not know, but thermoplastics has been featured in the past, so you can access that video presentation on the resources tab of 365. And I wanted to ask, do you think our inspection capability or technology, are we at a level where it is matching what you're talking about, the advances in technology, or do we need more help there?
I'm sorry, could you repeat the question?
I was talking about the inspection techniques, because as you mentioned something about the automotive and the volumes, but I think in this space environment, we're going to need more inspection.
Yeah, so we have Eric Burke on our series. He's really who I go to from NASA that can tell you, here's all the techniques that are available, here's the emerging techniques, and we absolutely are looking for new techniques all the time. And so that's an area both of development for us, and I think research for NASA on how you do both on orbit inspection, or I'll say more on vehicle inspection. So let's go do a macro scan of the vehicle and show that the tile's good through terahertz backscattering. Yeah.
Excellent. Thank you. And I know that's a very important topic for the SAMPE membership. So whether you're interested in attending one of the future SAMPE conferences or CAMX, you will see papers on that. Here's a question from Craig Chaffee. Dr. Polis, you said you don't do any thermal ABS, but what about using ecospheres for lightweighting, since they can be used for both?
So I'm guessing ABS here, he means for ablative systems. Um, that's interesting. I haven't really thought of that. We have other ways to change density for our tile. So we customize the density based on need. But I'll have to follow up, Craig, and look into Ecosphere specifically. But I understand the concept. I think for our particular tile, that might be hard to incorporate.
Thank you so much. Here's a question from Faride Selin Usta. What is the impact of using not fully cured polymers on outgassing properties of materials?
Yeah, good question. So again, we care very much about outgassing, especially on optical elements. So, we studied the effect on that. Again, if you think about, pure monomer versus just lower molecular weight or larger molecular weight between crosslinks, we're still cured. And so we didn't really have a problem there with outgassing for these systems. I think that was a very specific solution. So I don't, want folks to think, hey, we can go use this, for every application. But we had to be careful about outgassing, certainly for James Webb.
Thank you, Dan. Here's a question from Winston Hale. You mentioned MMOD benefits to Dream Chaser TPS. Could you speak to some of the trade factors between ceramics, FTPS, and metallics when dealing with MMOD risk mitigation?
Yeah, I mean, I probably can't get into that too much here, but in general, MMOD is a complicated trade between not just material density, but spacing, making Whipple shields and spacing those accordingly. Then backed by specific test data on those layers in combination to get the limit equations. And so there's a lot of testing, but one of the biggest factors is creating lightweight layers with separation rather than just, let's say, increasing the density through just material trades.
Excellent, thank you. Jaden, our PhD student from University of Nebraska-Lincoln, as secretary of TC7, did you have any question for Dan or any comment today?
Not really for Dan, but anyone can feel free to contact me. I should get back pretty quickly and I can help answer any questions that you have in the future.
I think that's an open call for join a future TC meeting. So again, you don't have to be a SAMPE member. We've designed these for maximum participation. We have friends from India on the call. It looks like Japan, China. So we're really grateful for all you taking time. But join one of the upcoming technical committee meetings and participate. That's what we're looking for. Thank you so much, Jaden. Dr. Fleming, I'm going to go to you again. Any comment or any remark, Chris, if you can?
Hello, can you guys hear me?
Yeah, we got you, Chris. So Chris is chair
of
the Space Applications Tech Committee. Thank you, Chris.
I'm so sorry. I'm having technical difficulties here, but I just want to thank Dan for a really awesome presentation. Dan's been instrumental in putting this series together. Something we've been trying to start for a while. So Dan, thank you for being the first and working through all the issues. And we have a really good series coming up, starting with Dan. Dan has some friends from NASA that are going to be giving similar talks. And I think a lot of the questions that I saw today hopefully will be answered through this upcoming seminar series. So Dan, thank you so much. Really appreciate your time.
Sure, happy
thank you all.
Yeah, this was excellent. Thank you for everyone for giving us an hour of your time. Don't forget, you're going to get a quick survey right after. It's very important. It's very short. It's just as easy as you registered, but just please complete the survey. And as I mentioned in the chat, Dan's presentation will be available by video. So we are able to share the video presentation maybe in 5-10 days. The team is preparing for CAMEX in Atlanta, several thousand folks coming, so a little busy on that, but you will see that on the SAMPE 365 platform under the resources tab, and you can also see some of the other presentations that are already available. So I'm going to close it out. If you have any questions or comments, feel free to get a hold of me, Raj Manchanda. I'm the Chief Technology Officer. It's Raj at sampi.org. But we're really grateful for your time. And you know, earlier in the chat, you mentioned where you folks are from. So once again, thank you. Joseph, I see your point in there about NDE, and everyone else. If you need any advice or something, joining the technical committee is a great opportunity. Dan, any closing remark?
No, I just really appreciate everybody that attended, and hope to see some of you at TC7 meetings. And Raj, thank you very much. Thanks to Jaden and Chris as well.
Excellent. Thank you, everyone. Have a great time. And the next webinar was just posted in the chat. You can also find it on SAMPI 365. Thank you, everyone. Have a good rest of the day. Goodbye.